how photochemistry can help treating cancer and acne with the same molecule? Before we dive into details, we need to understand some principles. And to do that, let's take a closer look at the sun. The sun is a gigantic sphere that produces a lot of energy, and this energy appears in the form of light. This light is essential for plants to undergo photosynthesis. But what is photosynthesis? This process enables plants to capture light energy from the sun and transform it into chemical energy in the presence of carbon dioxide and water. Plants can then synthesize sugar while releasing oxygen. And thanks to this process, they can grow, and of course, we can breathe. If plants can use light energy to carry out chemical reactions, why can't we use the same type of energy on molecules in the laboratory? In my research, I am especially interested in molecules called alkenes. An alkene is a planar molecule composed of two carbon atoms linked by a double bond. Each carbon atom can carry a chemical group. A special feature of alkenes is that they can have different geometries depending on the arrangement of their chemical groups. If the groups are on opposite sides of the double bond, the alkene has an E geometry. Conversely, if the groups are on the same side, the alkene has a Z geometry. It's like comparing different shapes. The E alkene is diamond-shaped, while the Z alkene is trapezoidal. Although these molecules have a similar composition, they differ in geometry, and are therefore called isomers. This geometry is very important as it can influence the molecule's properties and functions. Let's take a concrete example. Allyretinoin is a molecule possessing several alkenes. It is used in the treatment of cancer. If the geometry of the two surrounded alkenes is reversed, another isomer called isoretinoin is obtained. In this case, the molecule is used to treat acne. It is therefore essential to be able to control this geometry. But how can we do that? Let's take another look at our E and Z alkenes. Switching from one to the other is called isomerization. Since these molecules are similar, you might think that switching from one to the other is easy, but in fact it is more complicated. In general, it's easy to convert a Z alkene to an E alkene since in this geometry the chemical groups are far apart from each other, and this process requires only very little energy. On the other hand, it's more difficult to convert an E alkene to a Z alkene since a lot of energy is needed to force the chemical groups onto the same side. To clarify this concept, let's imagine a mountain. E to Z isomerization would be symbolized by a person climbing the mountain. His body will need a lot of energy to reach the top. Z to E isomerization would be represented by the same person going down the mountain. This time, the body needs less energy and effort to reach the bottom. The goal of my project is to perform the E to Z isomerization of alkenes. To do this, like plants and photosynthesis, we would like to harvest light and convert it into chemical energy. This process would allow us to control the geometry of alkenes and therefore influence their chemical properties and applications to treat cancer or acne, for instance, as we saw previously.